Hardware stores want you paying $12 for tubes of toxic adhesive that dry out after one use. But 10,000 years ago, humans discovered how to harvest waterproof superglue directly from pine trees for almost nothing. I just produced a batch of resin glue for $4 that bonds wood so effectively the fibers tear before the joint fails. This process allows a home chemist to bypass petroleum-based bottles entirely, using a few basic materials to turn tree resin into permanent bonds. The process involves engineering an open-source, infinitely reusable thermoplastic polymer. This material served as a primary industrial-grade sealant for millennia. The massive oak planks of 8th century Viking longships relied on this resin for structural waterproofing against the high-stress environment of the open ocean. Across North America, indigenous populations utilized the same chemical framework. You can see the thick, black pitch applied here to seal the seams of a birch bark canoe, providing a reliable, waterproof barrier. This illustrates the chemical conflict. Modern petroleum-based adhesives are thermosetting. They undergo a one-way, irreversible chemical cure, dictating a strict shelf life. Pine pitch, however, relies on thermal energy for its polymerization. This makes it a thermoplastic, capable of remelting and rebonding indefinitely. Short-lived, brittle synthetic adhesives are a commercial choice, dictated by planned obsolescence rather than a lack of better alternatives. Engineering this composite begins with selecting the correct botanical base. High resin varieties such as the ponderosa pine seen here, or the longleaf and eastern white pine, provide the most effective raw polymers. Resin functions as a tree's immunological defense mechanism, coating and rapidly sealing vascular damage with a liquid polymer. It is chemically distinct from the nutrient-transporting sap. This close-up shows the tree's vascular system oozing the liquid polymer specifically to protect a wound. Over time, these amber droplets will harden into a solid protective layer. Harvesting these already hardened chunks is the most sustainable extraction method, as it avoids disrupting the tree's active healing process. We use a knife to pry the dry lumps from the bark surface, ensuring we do not cut into the living cambium layer beneath. Avoid boxing or cutting fresh wounds into wild trees. This induces unnecessary botanical stress and leaves the tree vulnerable to pathogens. Hardened chunks are concentrated and stable. While fresh liquid sap is easier to work with, it must be collected passively to maintain ecological balance. Dead fallen pines serve as massive, freely available reservoirs of this raw material. In many cases, the wood is naturally saturated with solidified resin pucks. The living forest provides a self-replenishing supply of high-performance polymer bases that require no industrial synthesis to acquire. We melt the raw chunks using a double boiler to apply indirect, controlled heat. This prevents the resin from scorching or catching fire. We maintain a temperature window of 180 to 200 degrees Fahrenheit. This allows the resin to liquefy so that bark debris and impurities can be skimmed from the surface. Exceeding 250 degrees begins to degrade the essential terpenes. This releases acrid smoke and physically weakens the final chemical structure of the adhesive. Once purified and cooled, the pure resin forms a crystalline structure. While strong, it is also brittle and will shatter if subjected to sudden physical stress. This raw state is insufficient for engineering. To create a structural adhesive, we must modify the material's physical properties. The first modification involves creating a carbon matrix by mixing in finely crushed hardwood charcoal. In pure resin, a single fracture propagates instantly. By mixing pitch and charcoal in a 3:1 ratio, we introduce a rigid filler. These carbon particles physically arrest crack propagation. A microfracture hits a carbon particle and stops. We then introduce a plasticizer. Adding roughly 10% beeswax lowers the melting point and alters elasticity. The lipids separate the polymer chains, allowing the composite to survive the natural expansion and contraction of wood as humidity fluctuates. We calibrate the mixture by dripping the molten pitch onto a cold surface. We adjust the charcoal or wax ratios until the cooled material is firm but resistant to shattering. By combining a botanical polymer, a carbon matrix, and a lipid plasticizer, we transform a raw defense mechanism into a fully engineered biocomposite. This composite can perform high-strength repairs, such as fixing the broken tool handle that would typically require replacement or specialized commercial glue. We roughen the wood surfaces to increase the available area for mechanical bonding, providing more channels for the adhesive to enter. We apply the molten pitch while it is at its lowest viscosity. As it touches the porous wood, the cooling process begins the transition back into a solid. At this scale, we see the molten composite flowing deeply into the vertical channels of the wood's cellular structure. As the pitch solidifies, it expands slightly, creating physical anchors locked inside the wood. These keys prevent the joint from being pulled apart. This physical interlock is supplemented by a chemical bond, as natural rosin acids in the pitch grip the cellular fibers of the wood. During a destruction test, the bond is so integrated that the wood fibers themselves fail before the adhesive joint yields. This engineered biocomposite achieves a shear strength higher than the original wooden substrate. Ancient resin adhesives achieve higher strength than surface-level synthetics by structurally integrating into the wood's cellular matrix. The molten pitch can be cast into pucks for long-term storage. These solid units possess an infinite shelf life at room temperature. Because the cure is purely thermal, the material never expires. It can be stored for years and reactivated instantly with heat. This creates a perpetual cycle of use. If a joint needs adjustment or fails years later, it is simply reheated and rebonded. This chemical logic applies to various botanical inputs, enabling the creation of specialized custom blends. Different trees provide different mechanical properties. Spruce resin can be selected to maximize flexibility, while cedar resin offers superior rot resistance in damp environments. Mastering this process transitions the practitioner from a consumer of disposable products to a self-reliant home chemist. Modern design philosophies often rely on tool failure and replacement, but ancient engineering focuses on permanent maintenance and repair. Pine pitch replaces the cycle of disposable synthetics with a permanent, environmentally integrated repair system. Commercial adhesives rely on a cycle of disposal and replacement, but ancient resin technology offers a permanent, self-reliant alternative. Unearth the History focuses on the techniques that fall outside the patent system. Reclaim your tools, harvest from the source, and subscribe for more deep dives into the chemistry of the past.